Hey guys, so I'm going to do the first example in your assignment today. There are a few things that you're going to need for each of these ionic compounds. So today we're just worrying about, I'm giving you two elements and you need to be able to identify the valence electrons, the oxidation charge, so whether they will lose or gain electrons, and then you'll need to be able to use that information to determine the correct ionic formula for these bonds. Now, in these compounds. Again, if you didn't understand your ions or your Lewis dot lessons, you need to master those before you can do this, because you're going to be totally lost if you don't know where the charges or the valence electrons are coming from. Okay? So, let's go ahead and get started. I would have a periodic table definitely pulled up for me on P-table. Since I'm doing it on the dot camera today, I just went ahead and wrote down which group my elements are in, but of course you will be able to easily identify yours because you'll have P-table in front of you. Okay, so we have magnesium, which is an alkaline earth metal, and it is in group 2, and then phosphorus in group 15, which will be very important when we determine the valence electrons. Okay, so your 4 problems should look exactly like this one today. Like I said, I'm doing the first one for you, and then you will model your answers on your own sheet of paper and then upload it for credit. Okay, now let's start with our Lewis dot structures. Okay, so we are going to draw the Lewis dot structures for each element in the compound. So here we have magnesium, so I'm going to go ahead and draw my magnesium. And then we're going to have phosphorus. So I'm going to draw my chemical symbol for phosphorus. Again, comes straight from the periodic table. Now, we have to determine the number of valence electrons, right? Because if we're doing a Lewis dot, remember, Bohr models have all the electrons, but our Lewis dot only has the valence electrons. So remember, we determine our number of valence electrons based on the group that the element is in. And remember, the group are the ones that go up and down, the vertical columns. Okay? Magnesium is in group 2, so magnesium has 2 valence electrons. Okay? So 2 valence electrons for magnesium. So I'm going to go ahead and draw my valence electrons. 1, 2. And there is that Lewis dot for magnesium. Okay? Now let's do the same for phosphorus. Phosphorus is in group 15, also known as 5A. So that means he has 5 valence electrons. Okay, so if it's 5A, then you know it's 5. If you see it as group 15, you just drop the 1. So he's got 5 valence electrons. Okay, so now remember, with our Lewis dot, we start at the top and we work our way around, and we don't pair those electrons until after we have 4 of them around our chemical symbol. So 1, 2, 3, 4, 5. Okay, 5 valence electrons. So there is our Lewis dot of phosphorus and our Lewis dot of magnesium. Now, we know these can form an ionic bond because magnesium is a metal and phosphorus is a nonmetal. So magnesium is on the left-hand side of the table, phosphorus is on the right-hand side. So we know how to identify based on the position on the table whether something is a metal or a nonmetal or a metalloid. We've done that already. So magnesium, metal, phosphorus, nonmetal. So magnesium, because these are going to form an ionic bond, magnesium is going to donate his electrons to phosphorus, right? But we also know that because they are ionic bonds, these charges are going to have to cancel out. So we're going to have to figure out how many atoms of each element we're going to need in this ionic compound. Okay. Next, let's determine the charges. Remember, the charges are not the same as the valence electrons, but rather whether or not the element is going to donate those electrons or gain electrons. So we're going to use our valence electrons to help us determine the charges, but for these nonmetals, it's not necessarily going to be the same number as the valence electrons. So let's just keep that in mind. Okay. So for magnesium, magnesium is a nonmetal, or a metal. So metals donate. and they become cations, right? And the number that they'll donate is just their number of valence electrons. So it's easy, especially for the metals, to look at them and determine what their charge will be, because they're looking to get rid of their valence electrons, because they're looking to be stable. If they get rid of the valence electrons in their outer energy ring, then they'll be able to drop down to that energy ring before it, which will be full, which means it's a stable element. Remember, we're trying to follow the octet rule, where we want 8 electrons in our outermost energy shell, or in the case of the lower numbers, we want 2, because 2 is stable as well in that first energy ring, okay? So magnesium is going to get rid of his electrons. And if he gets rid of these electrons, remember electrons are negative, so if magnesium donates them, he becomes positive, right? So magnesium has 2 electrons to get rid of, so he's going to donate 2 negatively charged electrons. If he gets rid of 2 negatively charged electrons, that means the protons in his nucleus are now going to be the dominant charge, because they're positive. So he's going to have more protons than he does electrons. So the overall charge of this atom is now going to be positive. So the charge on magnesium is going to be 2+, because he got rid of 2 negative electrons. So the overall charge is going to be a 2+. Now let's take a look at phosphorus. Phosphorus is a nonmetal, right? So he's going to gain electrons, and he will become an anion, which is negative, right? If you take on negative electrons, then you will become negative. So now let's take a look. Now phosphorus, he has 1, 2, 3, 4, 5. So since he has so many electrons, it would be hard for him to kick them off, right? It would be hard for him to donate 5 of them to get down to a stable energy level. It's going to be easier for him to gain 3 than to kick off 5, right? So if he has 5, right, 8, which is where we want to be with the octet rule, minus 5 is equal to 3. So he's looking to gain 3 electrons, okay? So if he gains 3 electrons, he would be with a negative 3 charge, okay? So that would be his charge. So now we have our charges of our elements, and we have to put it all together, okay? So we've got our magnesium with our 2+ charge, and our phosphorus with our negative 3 charge. Remember, even though ionic bonds occur between ions, which have charges, the compound for the ionic compound itself has to be neutral, right? So we have to cancel those charges out, and we do that using the swap, drop, and chop, okay? So let's do the swap part. Our superscripts of our charges are going to become the subscripts of our opposite element. Okay, so our 2 superscript is going to become the subscript of phosphorus. Our 3 superscript of phosphorus is going to become our subscript of magnesium. Okay, we're just going to pull them opposite. This is also known as the crisscross or the lasso method. Okay, so now that we have our swapping, we're going to drop the charges. So we're going to rewrite the formula without the charges. So magnesium now has a subscript of 3, and our phosphorus now has a subscript of 2, right? Because 3 came from the superscript to here, and 2 came from here to here, okay? Now we have to chop. Now chop might apply and it might not, only if you can simplify these 2 numbers. And 3 and 2, they're not divisible, they don't share a common factor, they're not divisible by anything, so it's already simplified, so that's it. So our ionic compound is 3 atoms of magnesium and 2 atoms of phosphorus. And you can double check yourself too, because remember the compound itself has to be neutral. So if magnesium has a 2+ charge and there are 3 atoms of magnesium. That means in this compound, that would be 6 plus, right? And if there are, or phosphorus has a 3 minus charge, and we have 2 atoms of phosphorus, that would give us a 6 minus, 6 plus, and 6 minus. Cancel each other out for a neutral charge, so that looks good, okay? And that is how you determine the ionic formula for a compound or ionic compound.